Hello everybody, I'm Rosa Fera, a PhD student at the Department of Information and Electrical Engineering of Cassino, and today we are going to study and recall some elementary function that will be very useful in the mathematical analysis. And in this first lesson, we started to introduce a part of these functions, and we start from the polynomials. In detail, we can begin with the polynomials of degree 1 that are also known as linear function, and the reason will be clear in a few minutes. And then we will continue with the higher degree polynomials. In general, a polynomial over a field over the field R is a function P from R to the R that for every x in R associated the P of x that is the sum of A0 plus A1x where the coefficients A0, A1, An are real numbers. And this exponent n is the degree of the polynomial P of x. So a linear function or a degree 1 polynomial is a function of this kind where A and B are real number. This coefficient A is called angular coefficient because if we represent the point of the graph of this function, so if we consider a point P of coordinate x0 and ax0 plus b, this point is on a straight line that is the representation, the graphical representation of this function. And this is the reason why we call a degree 1 polynomial as a linear function. And this coefficient A is called the angular coefficient because it indicates the inclination of this straight line, and this is related to the angle that the line forms with the real axis of x, while this coefficient is the intercept because it gives the intersection of the straight line represented by this polynomial with the axis y, and the axis y of the Cartesian plane. So if we want to after we will give an example, and if we want to draw a straight line, we need only of 2 points of this line, and so then we have to connect these points. Okay, for example, let us consider this equation. If we consider the point A of coordinate x, the other coordinate is given by 2 times 0, that is 0, plus 1, that is 1. And we need another point, for example, the point of coordinate 1. And so the other coordinate is given by 2 times 1, that is 2, plus 1 is 3. So this is the point A. And this is the point B. Okay, as we see, this is B, this is the intercept of this straight line. And this is the graph of this linear function. Now we can continue with the linear equation that is strictly connected with the line. If we have an expression of this kind, where A is not 0, this is a linear equation, and if we want to solve this equation, we want to find a number x in R, so a real number, such that if I will substitute this number in this expression, I will obtain 0. And graphically, geometrically, this is equivalent to find the intersection point, the coordinate over the axis x of the intersection point between the line represented by this function and the axis y. So we can obtain a point of coordinate p x0, 0. That is the point intersection between this line and the axis y. For example, if we consider this equation, to find x, I have to bring this term on the right hand half side. So we obtain 5 for x equal to 5, and if we divide for 4, we obtain x that is 5 over 4, and it's easy to see that if I substitute this number in this equation, I obtain 4 times 5 over 4, that is 5, minus 5 is 0. And so this is a solution of the equation. Actually, this is the only one solution, because in general, when I have a degree n polynomial, I could have all at most n solution. So this is a linear equation, so a degree 1 polynomial, and so only at most one solution, 0 or 1 solution. I could also not 0 solution, but for linear equation it's easy to have always one solution. And instead of the equation, I could have also the inequality. For example, so if I consider the red terms, I have ax plus b greater than 0. Or if I consider the blue term, I have ax plus b smaller than 0. So I could have two kinds of inequality. And also I could have this symbol, greater or equal to 0 or smaller or equal to 0. The procedure are the same that for linear equation, because I have always supposing that a is not 0. For example, so if I have this inequality, I have to find a range of value for x, such that if I take a number in this range and then I substitute this number in this inequality, I obtain a number greater than 0. And this range, in this case, is this. So if I take a number greater than 5/2 and I substitute this number in this inequality, I obtain a number greater than 0. Another example could be in this case, I want to find a number such that I have to substitute in this expression, and I will obtain a number smaller or equal to 0. And this interval is given by x greater or equal to 4. So if I take a number greater or equal to 4 and I substitute in this expression, I am sure that I will true a number smaller or equal to 0. In particular, if I take 4, I have 4 minus 4, and that is 0, and it is also good for this inequality. Okay, that's it for the linear function, linear polynomial, and we can move to the degree 2 polynomials, also called quadratic polynomials. So a general expression for a degree 2 polynomial is the following. Where also in this case A, B, and C are real number and A is not 0. In this case, each degree 2 polynomial geometrically represents a parabol with the vertex V of coordinates minus B over 2A and minus delta over 4A, where A, B are the coefficients of the degree 2 polynomial, and this delta, called discriminant, is also an expression into the number A, B, and C, and it is equal to base B squared minus 4A times C. Delta is important because from delta we could say if this expression, if I put this expression equal to 0, I could have solution or not, and how many solutions I could have, because in this case I could have at most 2 solutions, 0, 1, or 2. And we have to distinguish to consider 3 different cases, because delta is a real number. First case is delta greater than 0, and in this case we obtain 2 real and distinct roots. And how to compute this root? X1 is minus B minus the square root of delta over 2A, and the second root is x2 equal to minus B now plus the square root of delta over 2A. So this is the reason why I need to have a positive delta. This is the general formula to compute the roots of this polynomial. So the aim is to compute the solution of and geometrically this is equivalent to find the coordinates over the axis y of the intersection between the parabol represented by ax squared plus bx plus c and the axis y. The second case is when delta is equal to 0, and in this case I obtain only one real root, and this root is equal to minus b over 2a, because if we remember this expression, when delta is 0, this square root is 0, and so I have only minus b over 2a. And in this case, the parabole has vertex x0, 0. The last case is when delta is smaller than 0. In this case, we have no solution. So, geometrically, the parabole represented by a degree 2 polynomial with negative delta has no intersection with the axis x. And now we could give some examples. So, we first compute the delta, that is 25 minus 4, a is 1, so we have 4 times 6, that is 24, and so delta is equal to 1, that is greater than 0. So we will have two solutions, two real roots, that are x1 is equal to 5 minus the square root of delta, that is 1, and so this is 1 over 2, and so this is 4 over 2, that is 2, and x2, that is 5 plus 1 over 2, that is 6 half, that is 3. So these are the two solutions of this equation, and if we want to represent this parabole, what we have to do? The vertex v is given to minus b over 2a, minus b is 5 over 2 is 5 over 2, and the second coordinate is given by minus delta, that is minus 1 over 4a, that is 4. So, this is the vertex, and 2 and 3 are the two coordinates over the axis x of the intersection point, and so the parabole is the following. After, we give an example also for the case delta equal to 0. This is 4 because it's the square of minus 2 minus 4 times a times c, that is minus 4, and so this is 0. In this case, we have only one solution. This one solution is given to by minus b, that is 2 over 2, so x0 is 1, and we know also that v, the vertex of the parabol represented, is 1, 0. So we have this parabol, and the last example compute the delta, that is the square of 2, that is 4, minus 4 times a times 3, that is minus 12, and this delta is minus 8, so this is negative. This means that no roots in R. So if we want to see the parabol represented by this curve, we have to compute the vertex. The test coordinates minus 1, and minus delta is 8 over 4, that is 2. This is the point V, the vertex V. This is the parabol that has no intersection with the real axis x. So as we did for the linear inequality, we could do the same also for quadratic polynomials and obtain quadratic inequalities. And also to this aim, the role of delta is fundamental, because from delta we could have different cases. So let us consider a general degree 2 polynomial where a, b, and c are real number. We know that delta is b squared minus 4ac, and if delta is greater than 0 and I want to compute the range of values for which ax squared plus bx plus c is smaller or greater equal to 0, or is in this case smaller equal to 0, I know that for positive delta I have two roots for this polynomial, and so we have to take the external value. So x smaller or smaller equal x1 union x greater or greater equal to x2, while in this case I have to take the internal values. If we take the previous example, when I want to find the values for which the parabole is over the axis x, so when x squared minus 4x plus 6 is greater or equal to 0, I have to take the value correspondent to over the real axis for this range. Because for this value I obtain that the parabole is over the axis to x. While if I want to find the values of x for which x squared minus 4x plus 6 is smaller than 0, so the parabole is under the real axis y, I have to take this value. If we remember that I called p of x squared ax squared plus bx plus c. If I want to find the values for which p of x is greater or equal to 0, in this case it's better to distinguish the single cases. In this case, I have all the real number x accepting the solution, because when delta is 0 I have only one solution, and for each x in R I have a positive value for the p of x, but when I put in p of x the solution, I obtain 0, and this is not good, so I have to eliminate minus b over 2a, that is the solution. While if I consider p of x greater or equal to 0, in this case I could take all the real number x. Instead, if I take p of x smaller than 0, strictly smaller, I cannot find a real number such that this inequality holds. So this is the symbol. And finally, if I take p of x smaller or equal to 0, when delta is 0, I have only the point x0 equal to minus b over 2a, because I cannot find the number x such that p of x is smaller than 0, but in this case I have also the equality, and the only case is when x0 is minus b over 2a. So if we take the previous example, in this case I obtain for every x in R and I could also represent this range over the real line. For this case, I have to represent R as this barrow, and the continuous line represent all the real number. While in the previous case, so if I don't want to forget, this could be represented in this way. This is the real line. I put 2 and 3 on this real line, and the first case is the following. While this second range is given by this. So I have to draw a continuous line under the interval right. So in this case, I have all the real numbers. Why? If I take x squared minus 2x plus 1 smaller or equal to 0, in this case I have only x equal to 1. This is the example. For all the real number x, this parabole is over the axis x and is never under the real axis. Only in this point 1, this is equal to 0. Last case, delta negative. When delta is negative, I have no roots, no intersection with the real axis. So the parabole is always over the real axis, x. And in all the three cases that we are analyzing, we suppose that a is a positive number. So the concavity is over the I, and this is satisfied for every x in R. Instead, the last inequality is never satisfied. So there not exist x in R such that this is satisfied. So if we consider the previous example, in fact, this parabole is always over the real axis x and never under the real axis. So we retrieve the range of value obtained. And when I have no real number, I could represent in this way. So, okay. Then we could have higher degree polynomials, and we have to highlight that when we consider degree 3 polynomials, in this case, we could have at most three real roots. And always I obtain one real solution, and the other two could be either in R or in the complex field C. And in fact, we have to recall these two different facts. The first, that a polynomial of degree n, as we said before, has always at most n roots. And the second thing is that every polynomial of odd degree has always one real root. For example, if I consider this polynomial, this polynomial has three real roots. You can check by yourself x1 equal to 3, x2 equal to -1, and the third is +1. So in this case, we have 3 real roots. While if we consider instead this polynomial has only one real root, that is x0 equal to 2. And the other 2 roots are in the complex field, because this polynomial could be also written in this way as x minus 2 times x squared plus x plus 1. So if I want to find the other 2 solutions, I have to find the solution of this polynomial, but the delta of this polynomial is 1 minus 4, that is negative. So this polynomial of degree 2 has no solution in R, but has 2 distinct solutions, complex and conjugate, in the complex field C. So if we want to give an example for the inequality also in this case, we could consider this polynomial. We have called this polynomial P of x. So P of x is the polynomial of the previous page. P of x greater or greater equal to 0, I have to put all the factors greater or greater equal to 0, and after I have to analyze a graph. So P of x is also x minus 3 times x minus 1 times x plus 1. I have to put all these factors greater than 0, x minus 3 greater to 0 or greater equal, x minus 1 greater or greater equal to 0, and finally x plus 1 greater or greater equal to 0. Okay, x greater than 3. Suppose that we want to solve P of x greater than 0. So I have to eliminate the point x. So P of x is the product of these 3 factors. In this range, for x smaller than minus 1, we have that all the 3 factors are negative, so their product is negative. In this range, we have that the first 2 factors are negative, so their product is positive, and multiplied by another positive number is positive. In this range between 1 and 3, we have that the first term, the first factor, is negative, while the other 2 are positive, so their product is negative. And finally, we have that all the factors are positive, so their product is positive. If I want to compute the range of x for which this inequality holds, so the polynomial P of x is greater than 0, I have to take this range that corresponds to x between -1 and 1 union x greater than 3. So these are the good range. Finally, to conclude about polynomials of degree greater than 2, we could recall another kind of polynomial equations that has the following form. And in particular, when n is equal to 2, where this n in general is a natural number. When n is equal to 2, I obtain the B-quadratic polynomials. So I have a and we could solve the related equation by reducing this kind of equation to a degree 2 equation. And finally, I have to solve another step that is the following. For example, if I take this B-quadratic equation, 4x raised to 4 minus 7x squared plus 3 equal to 0, I could set x squared equal to t. So with this position, I obtain 4t squared minus 7t plus 3. So this is now a degree 2 polynomial in the variable t. If I find the values of t, the root for this polynomial in the variable t, after I will have to pass to x by compute the square root of the values that I will find. So in this case, t1, 2 are equal to 7 plus or minus the square root of delta, that in this case is 49 minus 4 times 4 times 3 is 48, so this is the square root of 1 over 8. So we obtain that t1 is 7 minus 1 over 8, that is 6 over 8, that simplified is 3 over 4, and the second is 7 plus 1, that is 8, over 8 is 1. But these are the values in t. If I want to retrieve x, I have to find x1 is minus the square root of 3 over 4, that is minus the square root of 3 over 2, and plus square root of 3 over 2. And from this, we obtain x3 equal to the square root of 1 is or minus 1 or plus 1. So this is a degree 4 equation. I obtain 4 solutions, 4 roots. So the next step is to talk about systems. We could have a system of linear equation, system of inequalities of degree 1, 3, or higher degree. And so the main thing that you have to remember is that a system always stands for intersection of conditions. So the first example is are the linear systems, and I will be very fast on this topic. I only let you a system, an example. So solve this system is equivalent to find a couple of numbers x and y such that if I put x and y in both the equations hold. So from the first equation we have that if I want that x minus y is equal to 0, I want that x is equal to y. So if I substitute one of the variable in the second equation, I obtain so x is equal to y, 2y is equal to 1. So if I divide for 2, I obtain that y is equal to 1 over 2 and also x is 1 over 2. So these two numbers are such that if I put 1 over 2 minus 1 over 2, I obtain 0, and if I sum them, I obtain 1. Let us consider now a linear system of inequality, so a system of linear inequalities. For example, 2x minus 3 smaller than 0 and 5x greater or equal to 0. So first we have to compute the range of values for each inequalities, and after I have to find the solution that are good for both the inequalities. If I divide for 5, here I have to divide for 2, so I take x smaller than 3 over 2 and x greater or equal to 0. I represent on the real line. I have 0, and after 3 over 2, because it's bigger than 0, the first range is the following. And the second one is this. So in this case, I see that in this range, the first is not satisfied, while the second yes, and on the contrary, for x smaller than 0, I have that the second inequality is not satisfied. So the only range for which both the inequality are satisfied is this, between 0 and 3 over 2. Is this. And how to we could represent this analytically. So this is the solution range for this inequality, systems of inequalities. Okay, finally analyze a quadratic systems of quadratic equations. For example, so as we said before, for each quadratic inequality, I have to analyze the delta. In the first case, I have a positive delta, so I have two solutions. You can check by yourself, and I have two roots, -3 and -1. So the symbol is greater than 0, so I have to take the external values. So the range good for this degree 2 inequality is x minus smaller than -3 and x greater than 1. And for the second inequality also I have a positive delta. In that case I have to take the internal value. So the solution are 2 and 3, so I have to take the number between 2 and 3. And the common range is given by So in this case, I see that I have to take this range. So the solution range is x between 2 and 3. So before to leave the systems, we could analyze another kind of inequality, that is the quotient of polynomials. So quotient of rational function. For example, if I have this quotient, I want to find a range of values for x such that this quotient is greater or equal to 0. So in this case, I have to find, we do a convention in which I put all the members, so the numerator and the denominator, greater or equal for the numerator and strictly greater than 0 for the denominator. And after I have to analyze the sign of their quotient as done before. So in this case, I have another one, once again, a positive delta. So I have two solutions, and these two solutions are 3 and 4. So I have to take external value, x smaller than 3, union x greater or equal to 4. And for the denominator, in this case, I have to put greater than 0, not greater or equal to, because on the denominator I cannot have a 0 term. So the solution of this if I consider the associated equation, I obtain minus and plus 3. So I have to take the external values. So I have to take x smaller than minus 3 union x greater than 3. So for the numerator, I have that is positive for x minor smaller or equal to 3 and greater than or equal to 3 to 4. While for the denominator, so we have that for x smaller than minus 3, both the numerator and the denominator are positive, so their quotient is positive. Between minus 3 and 3, they are both no, this is smaller than 3, sorry. Okay, so the numerator is positive greater or equal to 0 for x smaller or equal to 3 and greater or equal to 4, while the denominator for x smaller than minus 3 and greater than 3. So for x smaller than minus 3, we have that both the numerator and the denominator are positive, so their quotient is also positive. In this range between minus 3 and 3, the numerator is positive while the denominator is negative, so the quotient is negative. Between 3 and 4, the same, but on the contrary, the numerator is negative and the denominator is positive. And for x greater or equal to 4, I obtain that the quotient is positive because numerator and denominator are both positive. So I have to take this range. So x smaller than minus 3 and x greater or equal to 4. So now we will pass to study another class of functions called irrational function. Whenever you hear irrational function, you have to think a root symbol, and the general expression for irrational function is the following. Where this number n is called index of the roots, and n is a natural number. The important thing that you have to keep in mind is that you have to distinguish when n is an even or an odd natural number, because in this case I have two different conditions on the g of x. So when I have a root with index n even, for example, square root, fourth root, sixth root, and so on, we have to put a condition on g of x. So g of x has to be greater or equal to 0. So I cannot compute the root with an even index of negative number. So you cannot compute in the real field you cannot find this number. In the complex field you could. While if I want, before to go on, we can give an example. So in this case, if I want to consider to compute the domain of this function, so the biggest range of values over x for which this function is well defined, I have to put, I have to solve the inequality x squared minus 4 greater or equal to 0. And since the solution of these, the associated equation of degree 2 is are minus 2 and plus 2, I have to take the external values. So x smaller or equal to minus 2 union x greater or equal to 2. So the domain of f is the following. And if we want to represent this function, so in this range we have no points of the graph of the previous function, because the domain goes from minus 2 to minus infinity and from 2 to plus infinity. And the graph is the following. As you can see, this function is always positive because it's always over the axis x. So in general, when I have an irrational function square when n, the index, is even, I always obtain a positive value. So we can also write this. When n is even, I have to put this condition, and after I have to put this condition, I have that this is not true in the case in which n is an odd number. So we can continue with the case in which we have an irrational function with an odd index. Okay, in this case, I have no condition to put on g of x, because if I have a cubic root or fifth root and so on, in general with an odd index, I can compute this root, because if I have a negative quantity under the root symbol, I have no problems. On the contrary of the even case. And so in this case, we have to observe that the root with an odd index of g of x could be also negative. And in fact, if we take this example, the cubic root of x as you can see, in this case, I obtain also negative values. For x smaller than 0, the graph of this function is negative. So the coordinate over the axis y are negative, while for x greater than 0, I obtain positive values for the values on the y-axis. So we have that f of x is greater or equal to 0 for all the x greater or equal to 0. Trivially, the domain of f is R. I have no points to eliminate. So now we could talk about irrational equations and irrational inequalities. And also for the equations and in the inequalities, I have to divide into two parts, when n is even and when n is odd. in this case, if I want to compute the solution for this irrational equation, I have to first put g of x greater or equal to 0, because anyway the root has no sense. And obviously also f of x has to be greater or equal to 0. And finally, I can raise odd members to the n power. So I obtain fx to the n equal to g of x. And so this is the general procedure. But now we give an example, some example. So consider the case in which f of x is the constant function. So this is f of x is equal to a real number. For example, square root of x plus 3 equal to 4. In this case, I have only two conditions, because f of x is 4, that is a positive number, and this condition is not useful. I have to put g of x, it's just satisfied this condition, greater or equal to 0, and after I have to raise to the power 2. So I obtain x plus 3 equal to the square of 4 is 16. So I obtain this system. I have two conditions. I want that x is a number greater or equal to minus 3 and satisfied this equation. So I have that x is equal to 16 minus 3, then that is 13. Since 13 is a number greater or equal to minus 3, I can accept this solution. So this is acceptable. Instead, if I want to solve this equation, has no solution because f of x is negative. The square root of x squared minus 4 equal to x minus 1. So this is g greater or equal to 0, x minus 1, that is f, greater or equal to 0, and finally x squared minus 4 equal to the square of x minus 1. The first inequality is satisfied for x smaller or equal to -2 or for x greater or equal to 2. And the second for x greater or equal to 1, and for the third condition I have to compute x minus 1 square, that is x squared minus 2x plus 1. To x equal to 4 plus 1, that is 5, divided by 2, okay, x smaller or equal to -2 or greater or equal to 2. So since 5 over 2 is in the good range, because I have to take only the number in this range, so greater or equal to 2, this is acceptable and is a solution. Now we give an example for the case n odd. In this case, I have no condition to put either or over G or over F. So I have only to solve this equation. So in this case, if I have the root with index 5 of x plus 7 equal to -2, I can compute this number x by raising all the members to the 5 power. In this case, I obtain -2 to the 5, that is x plus 7, that is equal to minus 32. And x is equal to -39. the second example. I have to solve this equation. And so this is the solution. And finally, we talk about irrational inequalities. In this case, the solution of these inequalities is given by solving two systems and finally by taking the union of the solution of both the systems. The first system is given by I have to put f of x greater or equal to 0, but also g of x, because we know that the root with even index is always positive, so I only could have the case of the root greater than a positive number, because this quantity is always greater than a negative number. And the last condition is the following. If I have greater here, I have to put greater here. If I have greater or equal in this inequality, I have to put greater or equal to in this inequality. And the second system is I have always to put f of x greater or equal to 0, because anyway I obtain no sense here. And in this case, when g of x is negative, I have not to put this condition, because this is satisfied. You could understand more in the following example. So the first system is x squared plus 4 greater or equal to 0 3 minus x greater or equal to 0, and x squared plus 4 greater than 3 minus x squared. Okay. This is satisfied for every x in R because x squared is always a positive number. If I add another positive number, I obtain always a positive quantities. So this is satisfied for every x in R, also here. While this second condition is x smaller or equal to 3. And the last this condition is x greater than 3 So in the first system, so I have to take this range. So I have the union between x between 5/6 and 3, union x greater than 3. If I represent this and then I compute the union, and after I have to add this. So the union is given by this range. So I have to take all the real number greater than 5/6. For sake of completeness, we give also this example. Okay. Sorry. In this case, I have an irrational function with even index greater than a negative number, and after I put the condition on on 3 minus x squared greater or equal to 0. Once that this condition is satisfied, all the inequality is always true. So this is equivalent to find the range of this inequality. And this is satisfied okay. We are again in the case of even index, but now we have the opposite sign. So we want to analyze this situation. In this case, I have only one system. And let's analyze an example. So I have to put 4x plus 7 greater or equal to 0, 3 minus 2 of x greater or equal to 0, and 4x plus 7 smaller or equal to 3 minus 2x all squared. Here is only greater. Okay, the delta of this is 16 minus 8, that is positive. So I have x1, 2, that is 4 plus or minus the square root of delta, that is 8, and so the square root is 2 plus 2 square root of 2 over 4. Is 2 minus square root of 2 over 2, and x2 is 2 plus square root of 2 over 2. So the system was x greater or equal to minus 7 over 4, x smaller than 3 over 2, and x smaller than 2 minus square root of 2 over 2, okay, because it's greater. I have to take only this range. Finally, we could analyze the case of odd index. In this case, is easier. This is equivalent to solve f of x greater or greater equal to g of x to the n. Examples. I have only to raise to the third power. This cube is equal to x cubed minus 6x squared plus 12x minus 8. So you obtain 6x squared minus 9x and plus 8 plus 4. Greater or equal to 0. The delta of the associated equations is 81 minus 96, that is negative. So this inequality is always satisfied. Last example on the irrational function. Also in this case, I have to compute the cube of 1 minus x, that is 1 minus 3x plus 3 x squared minus x cube. So we obtain 3x squared minus 3x squared plus 10x smaller than 0. It is equivalent to x times 3x minus 10 smaller than 0. Is greater now. Okay, this is a degree 2 inequality. We have two solutions, 0 and 10 over 3. I have to take the external value. So the solution is x smaller than 0, x greater than 10 over 3. So we concluded the part related to irrational function, and we are ready to study another kind of function that is called absolute value. And this function is defined over all the real number and has a particular feature. So the absolute value of x is a function defined over R and that has values in all the real positive number and is defined in the following way. The absolute value of x is x itself if x is greater or equal to 0, and is minus x if x is a negative number. So in both the case, either if x is positive or negative, I obtain a negative number, because if x is greater or equal to 0, x is positive. If x is negative, I take the opposite of x, and the opposite is positive. So for all x in R, the absolute value of x is greater or equal to 0, and the absolute value of x is 0 if and only if x is 0. And the graph of this function is the following. We have that in the first quadrant, it's the bisector y equal to x, and in the second quadrant is the other bisector, that is y equal to minus x. But in general, we find the absolute value not of x, but the absolute value of a general function f of x, and how it is it defined? If I have the absolute value of a general function f of x, this is equal to f of x for the x such that f of x is greater or equal to 0, and is minus f of x for the x such that f of x is negative. For example, if we consider the absolute value of x minus 4, this is equal to x minus 4, so f of x, if x minus 4 is greater or equal to 0. And this is equivalent to x greater or equal to 4, and is minus x minus 4, that is 4 minus x, in the opposite case, so when x is smaller than 4. And the graph of this function is similar to the previous, but the vertex of the v is not in 0, but in 4. So this is a translation one, two, three, 4. And this is the graph of this function. So if we want to solve a question with the absolute value, we have to make the following observation. First, if I want to solve this equation is not solvable. Why? Because we said before that the absolute value of x, or in general of f of x, is always a positive quantity. In this case, I'm searching for a number x such that if I put this number in this absolute value, I obtain a negative number. This is not possible, so this equation has no solution. Instead, this is the first example. The second one is the absolute value of 2x minus 7 equal to 3. So, in this case, I have first to split this function, because this is 2x minus 7 if 2x minus 7 is greater or equal to 0. So if x is greater or equal to 7 over 2, and is 7 minus 2x if x is smaller than 7 over 2. And so we obtain in this way two different equations, because in the case I have x greater or equal to 7 over 2, I have to solve 2x minus 7 equal to 3, and after I also have to solve this system x smaller than 7 over 2 and 7 minus 2x equal to 3. In the first case, I obtain 2x equal to 10. In the second one, two. So I obtain two solutions. In the first case, I obtain x equal to 5, and this is acceptable if 5 is greater than 7 over 2, and this is true, so this is acceptable. And in this case, when x is smaller than 7 over 2, I obtain x equal to 2. And also this root is acceptable. So I have two solutions, x1 equal to 5 and x2 equal to 2. We can give an important remark, because at the beginning of the lesson, I said that when I have a degree 1 polynomial, I can have at most only one solution. In this case, I have a linear equation, but the fact that I have the absolute value change the things, because in this case I obtain two solutions, both acceptable, and the polynomial is linear. So this is a strange things. And after analyze the equation with the absolute value, we could pass to the inequalities. So we start with the case of the absolute value of a function greater or smaller than a constant. And in this case, we have to divide into three cases. The first one is when the constant is positive, the second one when the constant is 0, and the third, the last, when c is negative. In the first case, I avoid all the procedures. The absolute value of f of x greater than c is equivalent to solve two systems. The first, in which f of x is greater or equal to 0 and f of x is greater than c, and union with the second system, f of x negative and f of x smaller than minus c. The case in which we have the absolute value of f of x greater than c when c is 0, this condition is satisfied for all the real number for which f of x is well defined, but I have to eliminate all the points for which f of x is 0, because when f of x is 0, its absolute value is 0, and 0 is not greater than c, because z in this case is c is 0. And so this is satisfied for every x in R minus the set of the x such that f of x is 0. And finally, the absolute value of f of x greater than a negative number is always satisfied. We quickly give two examples for these two cases. For the case of x c equal to 0, for example, if I put the absolute value of 5 plus x equal to 0, this is satisfied for every x in R, and I have to eliminate the x such that 5 plus x is equal to 0, that is minus 5. While in this case, for example, I could have this example. And this is satisfied for every x in R. And in detail, we could analyze an example for the first case, when we have absolute value of 2x minus 3 greater than 3. This is 2 minus x. And I have to solve these two systems. The first system is equivalent to solve f of x greater than c, and this is equivalent to find f of x smaller than c. So we have to find 2 minus x smaller than minus 3 union 2 minus x greater than 3. This is equivalent to minus x smaller than minus 5 union minus x greater than 1. This is x greater than 5 and this is x smaller than minus 1. So the union is given by this range mm. 20. Also, in this case, we have to divide into three parts. C greater than 0, and in this case is equal to the previous case. So we have to solve f of x smaller than minus c union f of x greater than c. In this case, what it is changed is that in this case, when I have greater or equal to c, this condition is satisfied for every x in R. For example, if I have the absolute value of x minus 4 greater or equal to 0, this is satisfied for every x in R. And when c is negative, I have also in this case for every x in R. And if I want to give an example, for this case, you can try to solve these inequalities, and for exercise you will obtain x smaller or equal to minus 1, x greater or equal to 1. Okay, in this case we have to solve these two inequalities, f of x greater or equal to 0 and smaller than c union minus c smaller than f of x smaller than 0. The case c equal to 0, in this case there is no x in R, and also in this case. For example, if I take I will add two examples. The first, if I have 3 plus 2x smaller than 0, I cannot find real number such that this is possible. And also, if I consider this example, also in this case there are no x in R. An example for this case, minus 1. Okay. Okay, and if I make the union, the first range is this. While the second is this. And so this is not included. So the solution is x between -1/3 and 1 included. Okay, last case. And in this case is the same of the previous page. What is changed is in the case of c equal to 0, because in this case I have only the points for which f of x is 0. While in this case is not possible. Examples. There are no real numbers, while in this case, if I have x squared minus 9, absolute value of this polynomial, smaller or equal to 0, I have to take only the points for which x squared minus 9 is equal to 0, and these are minus 3 and plus 3. And for the last case, that was the first case, I have in this case, we have x between minus 7 and minus 7 plus 1 is minus 6, while in this case, minus 8, x smaller than minus 7. And also in this case, when I make the union for minus 8, minus 7, and the biggest is minus 6. The first range is this, and the second is this. So the solution is the union of these two intervals, that is x between minus 8 and minus 6. Okay, these are all the 4 cases for constant function. We have a generalization. We have to solve these two linear system of inequalities, but not always linear inequalities. It depends from G and F. An example. So the first is x squared plus 2x minus 3 greater or equal to 0, and x squared plus 2x minus 3 greater than 1 plus 2x. Here I have f of x smaller than 0, so x squared plus 2x minus 3 smaller than 0, and the last is minus x squared minus 2x plus 3 greater than 1 plus 2x. So the first quadratic inequality is solved by x smaller or equal to minus 3 or greater or equal to 1, and second is x squared greater or equal to 0, greater than 0. The second system is for the opposite value, so x between minus 3 and 1, and in this case we have minus x squared minus 2x plus 3 minus 1 minus 2x greater than 0. In this case we have I changed the sign of all the terms and also to the symbol. So I have x squared plus 4x, 3 minus 1 is 2, that is minus 2, smaller than 0. This first system the solution of all this system is x smaller or equal to minus 3 or x greater than or equal to 2. Greater, strictly greater, because in this case is so here I have to cancel this. This inequality is satisfied for x between minus 2 minus the square root of 6 and x between minus 2 plus the square root of 6 is better. Minus 3. Okay. The first condition is this. And the second is x between these. And I have to take these small intervals, so and when I make the union, I go to to the next, no, I write in this page. The first system is this, but I have to add this part. So the whole solution is x smaller than -2 plus square root of 6 or x greater than 2. Finally, we described the exponential function. We know that when we take a real number that is greater than 0, I can generalize the power with the rational exponent, and I can obtain a function called exponential function and denoted with this symbol that is defined over the real numbers and that has positive values. And for x, a of x. In this case, the distinguisher is given by the basis of this power, because when a is greater than 1, we have that the exponential function a of x is an increasing function. This means that a of x is smaller than a to y if and only if x is smaller than y. Instead, when a is between 0 and 1, in this case I have a decreasing function. This means that if a of x is smaller than a to y, x is greater than y. We could see this property if we draw to graph. One of the most used bases in mathematics is a equal to e, where e is the Nepero number. This is an irrational number and is about 2.78 and other infinite many numbers. And in this case, if I consider this function, so this is the case of a greater than 1, I obtain this graph, and as you can see, this is an increasing function. Instead, if I take, for example, the function y equal to 1 over 2 to the x, I obtain this function that is a decreasing function, because when x grows, the function became more small, and from the graph you can also see that an important property is that a of x is greater than 0 for every x in R. Either if a is greater than is smaller or not than 1, but I have only to put a greater than 0 for have this property. And another property is that a to 0 is equal to 1 for every positive a. In fact, in both the graph I have that when x is 0, the function is 1, either here, that here. Okay, this function is a bijective function, so I can compute its inverse function. The inverse function of the exponential has a particular name that is logarithm. The logarithm function is defined as the inverse function of the exponential function, is denoted with this symbol, and when I consider the inverse function, the domain became the codomain, and vice versa, the codomain became the domain. So in this case we have that the logarithm function is not defined over all the real numbers, but only for the positive number, not 0, but has values in all the real numbers. So when I take an element y in R that is positive, the logarithm, I have to fix a basis a greater than 0. The logarithm in the basis a of y is x, and what this means? It means that a to the x is equal to y. So the logarithm respect to the basis a of y is the exponent x to give to the basis a to obtain the argument y. Okay. So in this case we have that the domain of, as observed, of log in base a is 0 plus infinity, and for the monotony the property are the same seen before. So when I take a basis a between 0 and 1, I obtain that the logarithm in the basis a is decreasing instead when a is greater than 1, the logarithm is increasing. Okay, now I will show you the graph of two distinct logarithms. As for the exponential function, also for the logarithm, it's very important to know the logarithm respect to the basis e, the Nepero number, and the logarithm respect to the basis e is also called natural logarithm and is denoted also with this symbol. While if I take the logarithm to respect a basis between 0 and 1, for example, the logarithm to respect to 1 over 3 of x, the graph is the following. Okay, some properties of the logarithm function. For every z in R, we have the and fixed a greater than 0 and different from 1. We have that these are the property of the inverse function is 0 and 2. If I take for every positive b and for every a greater than 0 not 1, a to the log in the basis a of b is equal to b. And the third property, if I have the logarithm in the basis a of 1, this is 0, because when I raise a to 0, I have always 1, and when I compute the logarithm respect to a fixed basis of the basis, I obtain 1, because the exponent that I have to give to a to obtain a is 1. And this is true for every a greater than 0 and not 1. Okay. Some easy computation. For example, if I fixed the basis to 3, the log in the basis 3 of 27 is 3, because if I compute 3 to the third power, I obtain 27. While another example, if I take the basis 1 over 2 of 16, this is minus 4, because 16 is 2 to 4, but to the fourth power, but 2 is 1 over 2 to the minus 1, so I have minus 4. And the other two example, for example, the logarithm to respect the basis 5 of 5 is 1, while the natural logarithm of 1 is 0. But here I can put all the bases. We are going to conclude, because we have to talk about equations and inequalities with exponential and logarithm function. I will give you some examples, and then we can conclude. So, I have this exponential equation. I write 8 as power of 1 over 2, and the exponent is minus 3. So since the exponential function is bijective, I can translate this equation into the exponent, and I have 3x minus 1 equal to minus 3, that is equivalent 3x equal to minus 2. So if I divide it for 3, I obtain x equal to minus 2 over 3. Second, if I consider 4 to the x minus 2 to the x plus 1 equal to 0. Well, 4 is 2 the square of 2, so I can write 2 to the x minus 2 to the x plus 1 is from the properties of the power, 2 times 2 to the x plus 1 equal to 0. If I put 2 to the x equal to t, I can rewrite this equation and I obtain a quadratic equation that I can solve. Respect to the variable t, this is easy because this is t minus 1 square equal to 0, and the only one solution is t equal to 1, but t is 2 to the x, and if I want to retrieve x, what I have to do, this is equal to 0, to x, and 1 is 2 to the 0, so this means that x is equal to 0. Now some equations with the logarithm. I have the basis 2 equal to 1. In this case, I have to see 1 as the logarithm in the basis 2 of a number. What is the number? The number is 2, because 1 is the logarithm to respect the basis 2 of 2. So I have to consider the same basis because anyway I cannot use the inverse function, and this is equivalent to find what? In this case, before I have to put the condition on the argument of the logarithm, because x minus 5 has to be greater than 0. So this condition is x minus 5 equal to 2. So I have to find a number greater than 5 such that x minus 5 is equal to 2. And this is 7. Since 7 is greater than 5, this is acceptable, so it's okay. And this is the solution. 4. The logarithm respect to the basis 1 over 5 of x squared minus 1 equal to the log respect to the basis 1 over 5 of 2x minus 4. In this case, I have to put the condition on both the arguments, so x squared minus 1 greater than 0, 2x minus 4 greater than 0, and finally I have to put x squared minus 1 equal to 2dx minus 4. The first is satisfied for x smaller than minus 1, x greater than 1. The second one for x greater than 2. And the equation is x squared minus 2x plus 3 equal to 0. To find the range, I have to compute the system between the first two conditions. This equation has solution x1 equal to minus and x2 equal to 1. What is the range? Sorry, in this case, the delta is negative because I have 4 minus 12, that is negative. I see bad because I see the next exercise, and this is not satisfied. So this has no solution. While if you want to check and you want another exercise with the solution, you can try by yourself the last exercise over the equations, that is the following. And you have to check that x1 equal to minus 6 and x2 equal to 1 are both acceptable. So for the inequalities, we need to remember only that the fact that when I consider the basis smaller than 1, I have a decreasing function. When the basis is greater than 1, I have an increasing function. So if I take these inequalities, 25 to the x minus 1 greater or equal to 0, 25 is 5 square, so I have 5 to the x greater than or equal to 5 to 1, that is 5 to the 0. And since the exponential function with basis 5 greater than 1 is increasing, this is equivalent to search x such that 2x is greater or equal to 0, and this is equivalent to x greater or equal to 0. Second example, 1 over 8 to the x minus 1 over 32 smaller than 0. In this case, the basis, what is? The basis is 1 over 2. 1 over 8 is 1 over 2 to the third power, and so I have 1 over 2 to the 3x minus, so I can write smaller than 1 over 32 is 1 over 2 to the 5. But in this case, the basis is 1 over 2, that is smaller than 1. So this function, exponential function, is decreasing. So I have to invert the sign, and I have 3x greater than 5. So x greater than 5 over 3 by dividing for 3. And the last two are two inequalities for the logarithm. In this case, when I have the logarithm, I have to put also the condition on the argument of the logarithm. So in this case, it's trivial because this is satisfied for every x in R. And -2 is the log respect to the base 1 over 3. I have to put here the what argument? I have to put 1 over 3 to -2, but this is 9. And in this case, the basis is smaller than 1, so this is a decreasing function, so this is equivalent to solve x plus 2 smaller than 9. So x squared smaller than 7, and since the two solutions of this, the equation associated is minus square root of 7 and plus square root of 7, I obtain the internal value. Last is 3, and the last is 4. I have the log to respect to the basis 2, that is x squared minus 5x plus 6, smaller than the log to respect to the basis 2 of x squared minus 3x. The first two, here I have to solve a system. The first two conditions are given by the argument of the logarithm. These are this quadratic polynomial greater than 0, also the second argument. And the last condition, since here the basis is greater than 1, is x squared minus 5x plus 6 smaller than x squared minus 3x. And the first two conditions are x smaller than 2 or x greater than 3. Here is x smaller than 0 or x greater to 3. And the last one is minus 2x smaller than minus 6, that is equivalent to x greater than 3. And to find the solution, we have to put 0, 2, and 3. The first is x smaller than 2 and greater than 3, x smaller than 0 and x greater than 3, and the last one, x greater than 3. So I have to take this part. And so the final solution is x greater than 3. And this example concludes our lessons. Thanks for the attention.